All right.
Serious stuff.
So we are essentially looking at what they call the substitution rule for integration. And the substitution rule is going to allow us to find these complicated integrals that don't meet that power rule. So we're going to look at trig functions. We're going to look at e functions. We're going to look at a's, natural logs, logs. So last week I kind of had you guys in groups sort of guess or try to manipulate them by working backwards from what you know about the derivative to try to find that antiderivative. And what we're going to do today is talk about exactly how to do it and how it has a u function of its own. So, just a refreshing, different way of looking at something. A definite integral is from an a to b numerical value. This is at the very top above the table. A definite integral is from a numerical value to another numerical value that gives a number as an answer. An indefinite integral has no upper or lower bounds and gives or yields what we call a family of functions. An indefinite integral is the case where you have to put a plus c. An indefinite integral can be represented by a slope field, which we're going to look at next week. Yes?
Yeah, diagnostics test we took with all the integrals and stuff. How much of that do you think we get right now?
A lot more.
Like right now?
Probably, there's only like 5 sections left that we have to cover. And then you've learned like all of calc. So yeah, a lot more. We're going to take, speaking of diagnostic tests, my goal is to try to really get your mock exam in within like the next 2 weeks.
When's the mock? Oh, okay.
So I wanted to try to teach you everything before I gave it to you, but the mock exam date is March 16th, and I want to have a day to go over all the multiple choice with you. So I'm thinking like late February, maybe a week or like a week and a half from now for mock exam.
February 24th. That's February 24th. Oh, wait.
Because of what?
Not 20%.
Alright. Gonna go with whatever day Mr. Mary approves. So, using differentiation, we can verify our natural log. So this is the case, we haven't already hinted on this because we did some of those problems where you had u to the -1, and then if you added 1 for your power rule, you got the 0, and I was like, oh no, like, we got 0, we can't have u to the 0, what's this case? And then somebody actually recalled that 1 over u, see? That 1 over u was the natural log of u. So, here's where we're going to get a little bit more particular and we're going to start talking about it a little bit more in depthly. The natural log has a domain that we need to take into account. And we have not really taken it into account yet. So the natural log has this domain where we know the natural log function and like what it looks like. So what we have to do is talk about what happens if the value inside this is positive versus what happens if the value inside it is negative. If the value is positive, absolute values are unnecessary. If the value is positive, absolute values are unnecessary. If the value is negative, when you antiderive the natural log of a negative u function, you must put absolute values around your u. So if it was a multiple choice question, they might give you an option with a u in absolute values and with a u without absolute values. So that's where even in that chart that I kind of gave you, it says see example 2. That's what we're talking about here. And then this is just me showing you, okay, here's the derivative, here's how we get back to it, here's why the absolute values don't matter. And I gave you that little note. Like I say, I note on absolute value, since the indefinite integral does not specify a domain, you should always use the absolute value when finding the integral of 1 over u. That means that the function natural log of u plus c is only defined on the positive u intervals, where the function natural log of absolute value of u is defined on both the positive and negative intervals in that domain. So what's the moral of the story? Pick the absolute values when it comes to the natural log. Okay. At the top of the next page, the question is the integral of f of u du the same as the integral of f of u dx? Is f of u du the same as f of u dx? Let's compare. The integral of f of u du, what did we say f of u was equal to? Cubed. So what's the antiderivative of u cubed du? If f of u is u cubed, but u is x squared, f of u could also be x squared cubed, right?
Keely, a court, please come to the office. Keely, a court, please come to the office.
Which would make this so now you have the integral of x to the 6th dx, because the bounds match. Does that give you the same answer? No. What if you compared their derivatives? Is that going to help you or get you to the same answer? Because f prime of u, even if I looked at it this way, is 3u squared. F prime of u with respect to plugging in x isn't 3x to the 4th. So even if I derived this, I'm not going to get 3x to the 4th either. So is f of u du the same as f of u dx? No. So why am I kind of going over this? Why are we talking about this? Well, this is the importance of matching your variables to your bounds, matching your bounds to your variables, and making sure that we are consistent in x's and dx's, that we are consistent with u's and du's. You cannot anti-derive an f of u when we're talking about dx unless we make a relationship between dx and du. So how could I get dx and du to have a relationship? Could I talk about du dx equals dx dx? In a way, right? So what would du dx be? It would be like
2x.
Yep. That's what I was trying to find my. And dx dx is kind of like your, yeah. So in this case, du dx and dx dx could have this relationship where we talk about deriving them, and then maybe we could go back and plug some things in and talk about how they do relate. So what I want to do is talk about how we can create that connection and where that connection comes in to the substitution rule. Yes.
Du over dx is 2x.
Because he took the derivative of x squared. But then he has to plug this back in to u. So he would still have to kind of cube it and talk about it. And that's what we're going to do, this exact example, but we're going to do it plugging everything in and starting by going through the substitution. So what we're going to do is replace a relatively complicated integral with something relatively simpler. This is the chain rule in reverse. So what we want to do is we want to talk about, okay, here's my u, right? So u is equal to x squared. We already just said du dx was equal to 2x. That means that if I wanted to isolate dx, that du is equal to 2x dx, but I'm trying to get rid of dx, right? And replace it with du. So, do you believe or understand that dx is equal to 2 du divided by 2x? So if I were to plug that in here now and say, all right, this is the same as f of u du all over 2x. Go back, and we're going to go look at the 1/4 u to the 4th plus c. We're going to talk about, okay, how does this f of u and 2x, normally the 2x's, there won't be an x. This is just an example to kind of like get you thinking. But we're going to talk about how we could plug this in and transform our functions so that they match. So let's start with something we can do easily in both directions. We have a square root, right? We don't have a chain rule yet. We have a power rule, but we could, like, well, it would be gross and messy. What's complicated about this problem? What could we take an antiderivative of if there wasn't something else? What do we want to get rid of? Not necessarily the square root, but what's under the square root. We know how to take the square root. So what we're going to do is we're going to say, all right, let's get rid of the complicated stuff. So we're going to make u equal to 2x plus 1. Exactly. Now, I've turned this into the integral of u, but here's that problem. We have the square root of u with dx, and we just said that f of u du is not the same as f of u dx. So I need to create that connection between them. I got to get rid of the dx and make it a du. So you're going to use differentials. Take the derivative of u. So that gives you du dx. Take the derivative of 2x plus 1. That gives you 2. Solve for your dx. So we're going to flip the 2 in the dx, so you get 1/2 du equals dx. Here's the substitution rule. You're going to substitute 1/2 du for the dx. What do you know about a constant within an integral? Well, you can bring it out in front. So I'm going to get that constant. I'm going to bring it out in front. And now I have the integral of the square root of u du. Now this is a relatively easy antiderivative. Add 1, divide by your new exponent. Dividing by 3/2 is really like multiplying by 2/3. So we have 1/3 u to the 3/2 plus c. Was my original problem given to me in terms of u?
No.
So substitution rule says I have to replace that u back at the end. So we're going to go back and we're going to say, all right, this is the same as 1/3 2x plus 1 to the 3/2 power plus c. Take your derivative of this. What's 3/2 times 1/3? 1/2. So take your chain rule, right? So you get 1/2, subtract 1 away, multiply by the inside derivative. Derivative of any constant is, so did I get 2x plus 1 underneath the radical? You see how your derivative of your antiderivative is the original function you started with? So again, all I did was check this is the check step. I checked what I did. Believing the u rule. Let's do another one.
So what's your answer? Is it 1/3?
1/2.
That's the answer. This is the derivative of the answer. Just checking to see that you got back to the original. This is just like a check.
1/3.
This is your answer. What's the complicated part of the problem?
You leave variables on the numerator.
Yeah, so we have the variables on top and bottom. It's a little complicated. But what we don't know how to do is the chain rule, right? So what's the inside function to the chain rule? That's what you want to make your u. You want to say to yourself, what's the inside part to my chain rule? What's the inner function? So in this case, the inner function is 1 minus 4x squared. What's the derivative of that? So I'm going to start getting into a habit. Instead of wasting my time writing du over dx, I want to treat it like we treated differentials. So remember differentials? It said, okay, you can put du on this side and dx on that side. So I'm just going to keep my dx over here. So I'm still taking the derivative of u with respect to x, so I'm just already pushing my dx over. If I plug my u in to the base, what x's am I left with? If I plug u into the base, yeah, I'm left with this, right? So that's what I need to substitute out. So I need to use this x and dx to substitute out this x and dx. So what do I have to get rid of over here to make that substitution or that direct link occur? Yeah, so what I need to do is divide by -8 so that I have x dx equals some stuff, but I can take away the x dx and replace it with some stuff. That -1/8 on the du is still your constant. So bring the constant out in front. Keep your fractions easy. Get them out of there. Do you see the connection? Can you go from the line to the line? Can you go from the x's to the du's?
Why don't you keep the x on top? Why does the x go with the dx?
Because you can't have a mixed variable.
Okay.
You always have to have u to u or x to x, but you can't have mixed variables in an integral. So I got to get rid of the x with the dx. So let's make this easier. This is -1/8, the integral. This becomes u to the -1/2 du. So now we're just back to a simple power rule, right? Add 1, divide by your new exponent. So you get -1/8 u to the +1/2. Dividing by 1/2 is really like multiplying by what?
2.
Can't forget that plus c because there's no bounds. So 2 times an 8 gives you a 4th. So you have -1/4 square roots of u plus c. Our answer wasn't given in u's to start. It was given in x's. So we have to change it back. By plugging in that u again. So again, think back to derivatives. We started easy, right? We had product rule, quotient rule, power rule, no problem. Got to chain rule, and it was like, oh, I got to remember all these simple steps. Same idea. We have the substitution rule. We just have to learn the steps. So what's the complicated or the inside function for the next example?
What's under the square root, which is 1 plus x squared.
Yeah, what's under the square root, which is 1 plus x squared. You know, if you got a u, when you're making the substitution, you need a du to find your derivative. So, all right, I can see this. I could say x to the 5th is like x to the 4th, x dx. So I could get 1/2 du equals x dx. And I could get rid of this by plugging in this. What am I going to do with an x to the 4th? How can I manipulate this function to get rid of an x to the 4th with what I know? Well, what could I do to this? Is it fair to say that x squared is u minus 1? We agree to that. What if I squared x squared? would it be fair to say that x to the 4th is u minus 1 squared? Can I plug that all in now and get rid of all the x's? Are we okay with that? You see all the plugging in? What did I create by doing that, though? I now have a function in a function. What can I do to u minus 1, though, that I could actually derive?
Boil it.
Yeah, FOIL it, right? Get it to an easier power rule. So u minus 1 squared is u squared minus 2u plus 1. Could I multiply that by the square root of u to get rid of a product rule? So square root times u squared. What do you do with your exponents? You add them. So 2 plus a half. One plus a half. What do I want to do with this ugly fraction? Bring it out in front. Can I antiderive that now? Yep. So, add 1, divide by your exponent. Add 1, divide by your exponent. So remember, dividing by like 7 halves or 5 halves is the same as multiplying by its reciprocal. Add 1. Divide by your exponent. Tag along with your plus c. Let's clean up our fractions by distributing the 1/2 and the problem didn't start as u's. The problem started as x. So you got to plug all the 1 plus x squareds in for all those u's. So 1/2 times 2 sevenths, your 2's will cancel. So you'd get 1/7, 1 plus x squared to the 7 halves. Minus the 2 would cancel. 2/5, 1 plus x squared to the 5 halves, plus the 2's would cancel, 1/3, 1 plus x squared to the 3 halves, plus c. You'll notice that when I distribute the 1/2, I didn't distribute it to the c. I don't multiply a constant or put a coefficient on that c value. The c value is always just c. The c accounts for the 1/2 in the antiderivative. The c does not ever, when we write an answer out, have a coefficient on it. So never write it as 1/2 c. Never write it as 1/4 c. Never distribute that value to the c. Does that make sense? this my chair example? No, you got a trick, don't you?
Yeah.
Right.
But you could have, what's the final answer? You just plug the x's in.
Mm-hmm.
That next one that you were on is on the next page.
My slides are just in it. I probably just like changed my order over time.
Yeah, it's good.
So we're on this one, right? What's the inside function?
It's the little
What's your derivative? What do I have on the derivative that I don't have in the problem? So divide both sides by 4. So I can substitute out the x cubed and the dx, and I can change this to a u. So you have 1/4 the integral of cosine u du. This is easy now. You know how to take that antiderivative. What's the antiderivative of cosine?
sign.
So you get 1/4 sine of u plus c. We don't want our answer in terms of u. To be honest, the trig stuff is easier than the polynomials. The trig is easier than the square roots and the chain rule that way, I think. Okay, let's look at the secant. What don't we like? Yeah, we don't like that it's 2 theta. So, u is 2 theta. Du becomes 2 d theta. We don't want the 2 because there's no 2 over here. So you divide by it. Get everything in terms of u's. And you have 1/2 secant u tan u du. So now 1/2 secant u tan u du just becomes secant u. Do you see why the 1/2 would cancel if you derived this? What's the chain rule say? It's 1/2 secant 2 theta tan 2 theta times the derivative of the inside angle, which is 2. So the 2 and the 1/2 would cancel, thus giving you the secant 2 theta tan 2 theta. Let's move my slide. Well, there. Alright. What's different about this one than the ones we just looked at?
This one down.
It has bounds. What's nice about this one?
Not add a C.
Okay. And this is example 1. We already found that antiderivative. We found it, right? We already said, okay, with no bounds, the antiderivative of this was equal to 1/3 2x plus 1 to the 3/2 plus c. So we found it without bounds. Already, we did that. I don't want to waste time finding it again with bounds. what I want to do is I want to talk to you about what happens when it has bounds and we have u substitution. So we have two methods we can talk about. The first method is to find the antiderivative in terms of u, get an answer, plug it back in, and get to your x's. So we could start with this. Get to this. Eliminate the plus c and put up our bounds, right? So what we did is we kept the bounds with respect to their original. So this is like saying x equals, and this is like saying x equals. So we went back to the x's because those are x equal values. So now you plug them in. So you say, okay, I have 1/3, 2 times 4 plus 1 to the 3/2 minus 1/3, 2 times 0 plus 1 to the 3/2. Do you see why I said a long time ago you had to always plug in your zeros, because eventually it's not always going to zero out? So 2 times 4 is 8. 8 plus 1 is 9. The square root of 9 is 3. 3 cubed is 27. 27 divided by 3 is... I have lead. Do you need lead?
Oh, yeah.
Give me 1 second to finish this out. I have a good case of it. Okay, 2 times 0 is 0. 0 plus 1 is 1. Square root of 1 is 1. 1 cubed is 1. So you have 9 minus 1/3, or 8 2/3. Here's what I want to do. I want to go backwards a line. Is it 0.7?
Yeah.
Oh, you have blood for
I just cooked them up.
Oh, I was like, yeah. All right, here's what I want you to do. I want you to go back to that example 1, and I want to change it. I want to talk about the answer before we plug the x back in. So I want to talk about what we got in terms of the u's. So when we plugged in our u's, we had 1/2 square root of u du, right? And that turned into 1/3 u to the 3/2. How could I change these bounds to match u's instead of x's? So what we can do is, if we want to keep our problem in u's, because it's a definite integral, is I was originally told u was 2x plus 1. And I was originally told we're evaluating when x is 4. So I want to say, all right, what's u of 4? It would become 9, right? So now, if I wanted to evaluate this with respect to the u's, my upper bound would become a 9.
So you're lower bound 1/3 now?
So if I plugged in u of 0, not 1/3, it would become 1.
1. Yeah.
Because it's 2 times 0, which is 1. So this bound here would change to a 1, which means this would be a 1. So now plug in 9 for u and plug in 1 for u. Do I get the same answer? The square root of 9 is 3. 3 cubed is 27. 27 divided by 3 is? Should get me the same answer. If it doesn't, I did my math wrong.
Oh, yeah.
But the idea is that there is actually questions on there that are called change of bound questions. And it's really just use substitution. So you're changing the bound from one to the other based on what you started with. Let's look at the next example. We have 1 to 2. We didn't already do this one, so you got to do all the work for it. What's the inside function?
3 minus 5 is
What's the derivative?
-5 dx.
Do I have a -5 anywhere over here? No, so I got to divide by it. What I want to do is essentially change my bounds as I do the problem. So we're going to change the upper and lower limits. And we're going to change it now when we do the u's. So that means I need to know what is u of 2 and what is u of 1. So u of 2 and u of 1. So when I do my u sub, I want to immediately just sub in my new intervals. So we're going to plug in the -1/5. I'm going to change my limits to the -2 and the -7. I'm going to replace my u and du's. So I get u to the -2 du.
Don't you have to flip the signs because it's opposite now?
It wouldn't matter. This negative here kind of accounts for that. If I wanted to flip them, I could, but I'd have to take away my negative. It doesn't matter if you're going from left to right or right to left when you evaluate. But if you wanted to, you could. You would just eliminate the negative on the 5. So you could say 5, or negative, or positive 1/5 rather, from -7 to -2. And that's that rule about flipping them. But if you watch, it won't matter that I have to do them in reverse. So you get -1/5. What's the antiderivative of u to the -2? What's the rule? Yeah, it becomes -u to the -1 or -1 over u. And we're evaluating from -7 to -2. What happens to a negative times a negative? So we get 1 over 5u from -7 to -2. So we get 1 over -35 minus 1 over -10. Which, honestly, with the people like that, as a decimal, it's like 0.0714, so it's super tiny. Let's compare it to if we had done it with the x's. Where would you have changed, or what would you have changed? You would have to have back here, right? So you got your antiderivative with respect to u. So it would have been -1/5, negative, and then would have plugged 3 minus 5x to the -1 back in. And I'd have kept my bounds from 2 to 1. Do you see how this is going to be a lot more complicated to plug into? than when you just find your bounds here and change them. Because what you're doing is you're simplifying this process of plugging in to the 3 minus 5 times 2. So by changing your limits, your N1, you're not giving yourself the opportunity to forget to plug back in the right limits or to plug back in X. A lot of times what people do is they'll leave it from 2 to 1, and they'll plug the 2 and the 1 into U instead of turning it back to the X function. So stick to a method, get used to it. However you start it is how you want to continue to do the problems. So if you change your use always, change your use always. If you change your use never, change your use never.
So you can always do those problems just by changing the limits.
Mm-hmm.
There's no problem where it's like...
You can always change your bounds. Okay. Your homework's going to be in your book. Give me a second.